Hey everybody, this is lesson 3 in unit 5. We're looking at sum and difference identities today. In this section, we're going to use formulas that involve sums and differences to verify some identities. The main thing you want to do is look for patterns to see that could help you memorize these formulas. I've got them grouped by their angle, whether I'm having the sine of two angles or the cosine of two angles, or the tangent of two angles. One interesting feature to notice is how the alpha and beta angles either change or alternate. So in the first two with sine, you notice that if sine is the sum of two angles, that the expanded form keeps the sum, and difference keeps the difference. But it switches with cosine. If cosine is added, then expansion causes subtraction, and vice versa. If the cosine is the difference of two angles, when we expand, we switch to addition. Now, tangent has two things going on. We have addition for the sum of the two angles, so addition stays in the numerator, but subtraction in the denominator. And here, subtraction on the two angles means subtraction in the numerator and addition in the denominator. Another key feature that you might see is, for example, the sine of two angles. The pattern is sine, cosine, cosine, sine, but the cosine of two angles keeps the trig functions grouped. Cosine, cosine, sine, sine. And then the other important fact is that the alpha and beta alternate. Alpha and beta alternate. Alpha and beta alternate. So if it's sine, cosine, cosine, sine. And if we have cosine, it's cosine, cosine, sine, sine. Sine keeps the argument in expansion, and cosine changes the argument to subtraction from addition, or addition from subtraction. So just some key things to look for. In example 1, we're going to take the exact value of cosine 70, cosine 40, plus sine 70, sine 40. So to rewrite that, when it's cosine, cosine, sine, sine, that means we're taking our angles of 70 and 40 and the expanded pattern formula had addition. So when we condense, we're going to subtract. So these two angles, cosine 70 minus cosine minus 40, is going to be the cosine of 30 degrees. And on our unit circle, the cosine of 30 degrees is radical 3 over 2. Here's two more to practice that way. In the first one, we've got sine, cosine, cosine, sine. So that's going to be the sine argument. And there's addition here in the middle for the expanded. So we want to add 22 and 13 to find we're looking for the sine of 35 degrees. And without taking a calculator out, that's as far as we can go to write the expression as the sine of a single angle. This one's the cosine pattern because it starts out cosine, cosine, sine, sine. We have addition in the middle. So this one would happen to be the difference between pi over 3 and pi over 4. So in this case, with radians, we want to get a common denominator. That would be 4 pi over 12 and 3 pi over 12 to have a common denominator of 12. And combining those two fractions, we're looking at the cosine of pi over 12 as a single angle. For example 3, we want to use the fact that cosine of 15 can be found using 45 degrees and 30 degrees. These are two values on our unit circle. So to rewrite cosine of 15 degrees, that could be cosine alpha, cosine beta, and then this is minus, so expanding we're going to add, and then sine alpha, sine beta. So cosine, cosine, sine, sine. We're alternating 45 and 30. And next we want to actually evaluate each angle. Cosine of 45 is radical 2 over 2. Cosine of 30 is radical 3 over 2. Sine of 45 is the same as cosine of 45. And then sine of 30 is 1/2. So simplifying all of that, we have square root of 6 plus square root of 2, and it's divided by 4. Now you notice between the sums how we have the square root of 2 as a common factor. You can also rewrite that as square root of 2 and then leave square root of 3 plus 1 and divide that by square root of 4. So either one of these answers would be appropriate. Just depends on what your teacher prefers. In example 4 and 5, we're going to look at verifying two identities by using the expansion properties or the sum and difference formulas. So let's, for example, expand cosine of alpha minus beta. So we got cosine, cosine, and it's minus, so we're going to change it to addition. Cosine, cosine, sine, sine. And we have cosine alpha, cosine beta for a denominator. And just to save time, I'm going to say we're trying to get that left side over here, okay? So let's see where that goes. Now, in this case, I want to decompose the fractions and make two separate fractions because I'm looking at my answer and I want a 1, and I can see that cosine alpha, cosine beta is set up to be a 1 if I break the fraction apart and put it back to two separate fractions with that common denominator, cosine alpha, cosine beta. So that's the first thing that we want to do. And then you can see that cosine alpha, cosine beta becomes that 1 in our answer. And then I want to break these apart and make it become two separate terms, since we have a sine and a cosine for the alpha angle. Could group those together, and then a sine divided by cosine using the beta angle. And that's going to give us what the right side had. This is the tangent of alpha times the tangent of beta. So both the left and the right side are now in agreement, and we have demonstrated what we were asked to do. Show that they were equivalent, left and right side. Example 5 is one for you to try. So you could turn the video off and come back and check if you like. Expanding sine of pi over 2 minus x would be sine, cosine, keep subtraction, cosine, sine. And we want to know, is that equivalent to just cosine? So sine of pi over 2 is 1 times cosine, and cosine of pi over 2 is 0. So 1 minus cosine, 1 times cosine is cosine, and cosine minus 0 is definitely equal to cosine. So again, we've demonstrated what we were asked to show, that the left side, using the difference formula for sine, is equivalent to cosine. Here's another one that is using the fact that 5 pi over 12 can be represented as 1/6 of a pi and 1/4 of a pi. So expanding using those two angles as our alpha and our beta angle. The pattern is sine, cosine, cosine, sine. Sine, cosine, keep plus, cosine, sine, and evaluating each term. That's 1/2. This is square root of 2 over 2. This is radical 3 over 2. And then sine at pi over 4 is radical 2 over 2. So again, we have square root of 2 plus square root of 6. Getting ahead of myself there. Square root of 2 plus square root of 6 divided by 4. We have a common denominator of 4. I'm not going to factor it. I'm just going to combine them together. So example 7 is one for you to try. And then come back and check that you can expand your cosine of pi over 4 plus pi over 3 would give you 7 pi over 12. And expanding is cosine, 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 sine, sine. But addition means we subtract when we expand. And then go back and evaluate for each trig function. Cosine pi over 4 and sine pi over 4 are both square root of 2 over 2. But cosine at 60 degrees is 1/2, and sine at 60 degrees is radical 3 over 2. We have subtraction. So again, square root of 2 minus square root of 6 divided by 4 is the cosine of 7 pi over 12. So that's the exact value of that. Now, example 8, we're going to be given some information, and we're going to have to resolve those triangles. So sine of alpha is 4/5, and we're in quadrant 2. So we've got a triangle over here. Oop, that's not a very good line. Okay. A triangle over here in quadrant 2. This is our alpha angle, and sine is opposite over hypotenuse, which makes this a 3, 4, 5 triangle. So we would go negative on x, positive on y. Then sine of beta, beta's in quadrant 1, and beta has opposite to hypotenuse. So radical 3 is on the x-axis. Now for part A and B, we've got the cosine of alpha is cosine is adjacent to hypotenuse, and cosine of beta is adjacent hypotenuse. So we got negative 3/5 and radical 3 over 2. We have 4/5 for sine of alpha and 1/2 for sine of beta. And we're going to look at cosine of alpha plus beta on this next page. So cosine of alpha plus beta is going to be cosine, cosine, sine, sine. So cosine, cosine, sine, sine. Did alpha, beta, and it was sum, so expanded, we're going to subtract. And we said cosine of alpha was found from drawing the triangles. That was negative 3/5. Cosine of beta was radical 3 over 2. And then the sine of alpha was given to us. That was 4/5. And the sine of beta was given to us. That was 1/2. So simplifying that, we have negative 3 radical 3 minus 4 in the numerator and 10 in the denominator. So this is our exact value for example 8a. And then example 8, that's example 8c. We did the A and the B. And then example D is going to be sine of alpha plus beta. So expanding that, we've got sine, cosine, cosine, sine. So when our sum is the sine of two angles added, we keep the operation of addition and we alternate sine, cosine, cosine, sine with the alpha and the beta angles. And we said sine of alpha was 4/5 and sine of beta was 1/2. Those were the two things that were given to us. The cosine of beta was radical 3/2. And the cosine of alpha was negative 3/5. And we're going to add those together and simplify. So our complete answer, exact answer, is 4 square roots of 3 minus 3 with a common denominator of 10. And that's finding sum and difference by making a sketch and locating the missing information. Now on our last few examples, we want to use those reduction formulas to prove, we want to prove a reduction formula. And we're proving that the sine of any angle plus 180 degrees is going to produce the opposite of sine, or the opposite of that angle. And we can use the expanded pattern for sine of the sum of two angles, which is sine, cosine, plus cosine, sine. And we want to know, is that equivalent to negative sine? So the sine of x times the cosine of pi is going to be sine x times negative 1. And cosine of x times the sine of pi is 0. So those two terms are going to go away because that's gone. And we have proven that the sine of any angle plus 180 degrees is going to be the opposite of that angle. And it should say equal, not plus. So we did demonstrate and prove what we were asked to prove. And then here's one for you to try, and you can come back and check your answer. Expanding the left, cosine, cosine, and then minus sine, sine. We want to see if that's equivalent to sine because we've added 270 degrees to our cosine angle x, whatever that is. So the cosine of x times the cosine at 270, that's 0. So this is gone. That whole term's gone. And this is the sine of an angle, and the sine of 270 is negative 1. So is that equivalent to just positive sine? And this is minus a negative. So yes, it definitely is equivalent, that the sine of x is equal to the sine of x. So we have proved this reduction formula. If you have the cosine of any angle plus 270 degrees, that sum is really the sine value right there. And then our last example is using the tangent formula, and we've got to show that the angles 2 pi over 3 and pi over 4, if we subtract those angles, because 2 pi over 3 with a common denominator of 12 would be 8 pi over 12, and pi over 4 with a common denominator of 12 would be 3 pi over 12. So if we subtract those, we'll get the 5 pi over 12 that we want, right? So we want to use the tangent of 2 pi over 3 minus pi over 4. And that formula, when it was minus, we kept minus in the numerator, so tangent of 2 pi over 3 minus tangent of pi over 4. And then the denominator, we switched signs and had 1 plus tangent 2 pi over 3 times tangent of pi over 4. So we just need to evaluate each trig function. This is going to be negative radical 3, and tan of pi over 4 is 1, so we got negative radical 3 minus 1, and this is 1, and we have negative radical 3 again times 1. And putting all that together, we've got negative radical 3 minus 1 divided by 1 minus radical 3. So normally we would want to rationalize the denominator by using the conjugate of the denominator, which is 1 plus radical 3. And then using distributive property, we're going to get negative radical 3 and negative 3, and then negative 1, and then negative radical 3 again. In the denominator, we've got the difference of 2 squares, so that's going to be 1 minus 3. And then combining like terms, it looks like we have 2 negative radical 3's and then minus 4. So negative 4 minus 2 radical 3 divided by negative 2, and then bringing that negative up to the numerator and simplifying. 4 divided by 2 is 2, and then 2 radical 3 divided by 2 is positive radical 3. So we've simplified that expression using the tangent of 5 pi over 12. This is the exact value for tangent 5 pi over 12. That's the end of lesson 3, and I'll see you next time with multiple angle identities.